Good day, everyone. This is our first topic about simple stresses. You know, under this lecture, uh, I'll be discussing about the machine designer's responsibilities, the philosophies of design, the stress, the tensile and compressive stresses, tensile strength and yield strength, the modulus of elasticity, and the factor of safety. Like the famous adage, necessity is the mother of invention. Every machine is born out of real or imagined need for it. This idea may then evolve into a conception of methods and process in order to accomplish the purpose. What follows may be the arrangement of parts, the location and lengths of the links, which may include the kinematics of the machine. So you'll know about the kinematics that only considers the motion of all the linkages and parts of a mechanism or a machine, as well as the basis for gears, bolts, springs, cams, and other elements of machines. The practice of designing is applying combination of scientific principles and judgment based on experience. In other words, it is a combination of theoretical and empirical knowledge. Theoretical is what we read in the book, and empirical is based on experience or experimental data. We always think of an invention as something or someone who starts from scratch and then creates a new design and machine. What we don't know is that even though the inventor has created a machine we have never seen before, they use ideas that have already been known, and it is used in combination with other components, other concepts, ideas that are already available. Most designs follow a pattern familiar to and typical of an industry, whether it's a car, a sewing machine, is a washing machine, refrigerator, are seemingly similar to the previous one. So, in other words, uh, in the design, while there are improvements, there are the new versions or the new models are seemingly similar to the older ones. Changes were introduced either for the purpose of improving the machine, the efficiency, or gain an economic or competitive advantage. What's the purpose of improving or adding some essential parts of the older versions into the newer one. This philosophical approach may depend upon the kind of industry or the type of machines. For example, in the airplane industry, where lightweight and reliability are of utmost importance, the design philosophy will lead to high precision designs. The product is manufactured and operated under actual or simulated conditions, perhaps repeatedly, until obtaining an acceptable design. In the automotive industry, the design of the automotives is suitable for mass production. Uh, the assembly or the sub-assembly design, which involves the automobile, are to be produced in vast quantities, which will be tested under actual operating conditions. Because the errors or the so-called debugs need to be eliminated before the mass production begins. So they're just like the airplane industry and as well as to the other industries involving machines. The design should involve testing either in simulated or actual operating conditions so that they will find out the errors and thus eliminating the errors before the production or actual operation begins. Machine design is engineering. Design of machine elements begin with calculations. From unknown data such as the work done or power consumed. We measure those for a sequence of positions of machine cycle using the principles of mechanics. Then each element is designed so that it will perform uh, uh, so, uh, so that it will perform its function without failure. In doing so, we will use the principle of strength of materials. So we have completed the course strength of materials. So the knowledge you have gained from strength of materials will be used in or applied in solving engineering problems. And thus in this machine design, you will use the principles to find suitable dimensions of machine elements. And in the process, the designer does a stress analysis. So with this stress analysis, it will involve design in the various parts of the machine elements that is subjected or are subjected to maximum. Stress analysis is an essential process or essential part in the machine design. So most important is the judgment. It is seldom possible to use theoretical equations to determine and adapt the result right away. So designer must use their judgment to decide calculated dimensions, dimensions, type of material from suggested from the book is practical accordingly in real life. So it is in the prerogative of the designer, you decide to judge if the calculated figures are practical in real life. So now let's go with stress. So already known this stress in your state materials and that you'll be encountering most in this course. So it is uh, this course the the term stress refers to the unit stress which is measured in pounds or kips per square inch. Okay, so this kip is a unit of force that is equivalent to 1,000 pounds. Kip is actually a contraction of kilopound. So instead of saying kilopound, it is contracted into kip. All right. So these are the for the tensile stress and compressive stresses. So and stress is denoted by small letter s, and tensile and the compressive stresses are denoted with the T and C respectively. So since stress or unit stress is equal to the applied force or applied load into a cross-sectional area, so the load is represented or denoted by F and the cross-sectional area is A. Throughout the majority of this course, you'll be using these units. So these units for stress, PSI or KSI will be used throughout this course. Our general assumption here is that the load F's or the force, the line of action is at the center of this course. We'll be assuming that the location of the application of the load is at the center of the cross section or the centroidal axis. So meaning no scattering of loads along the cross section, thus it will be concentrated at the centroidal axis of the cross section. In the above figure, when a bar is in tension, the force F or the load F is applied outward and it tends to elongate the bar. And thus, this tendency of elongation of the bar has effects on the area and on the geometry of the bar. For below figure, the load F is applied inward. So in force, the forces tend to shorten the bar. Now let's take a closer look to the bar when applied with a compressive or tensile loading. The bar or any member when subjected to the action of a force will be deformed. So as you can see, the bar was applied with the with the tensile loading. So you can see exaggerated. There is an effect in the geometry, or particularly the cross-sectional area of the bar. This deformation not only affects the length, not only have the tendency to elongate the specimen, but also the area of the cross-section. A specimen subjected to tensile loading elongates and decreases its cross-sectional area. In contrast, when subjected by compressive loading, the specimen shortens and the cross-sectional area has a tendency to increase. This change in length is called yield or deformation, denoted by the Greek letter delta. And the deformation per unit length of the specimen is this for a percentage increase or decrease in length. And it is delta L over L naught, where delta L is the total elongation or the change of L naught is the original length of the specimen. Ultimate stress or the tensile strength are at the highest point on the stress strain diagram or the curve. So this figure is a stress strain diagram. So in this stress strain diagram, this represents the curve that a specimen will undergo from the proportional limit until its fracture or its breaking point. Okay. So in the stress strain diagram, the highest point in the curve is the so-called ultimate. So as you can see here, it is represented point D. This is the stress at which a specimen undergoes a marked elongation or deformation without increase in load, and it is from the point B to C. Okay, so as you can see, there is a significant increase in this. So it means that there is a marked elongation of the specimen. So thus the points B and C are the so-called the yield stress points. The upper and C is the lower yield stress points. Okay, so at these points in B and C, the specimen will start to deform, and when a specimen starts to deform, it will not return to its original length. Okay, so at what point in the stress strain diagram shall the specimen can elongate or deform, and it can return to its original length. So what we called as the proportional limit. Okay, so as you can see here in this in the figure, this is a stress strain diagram of um, several engineering materials. So we have here soft steel, aluminum alloy, heat-treated alloy steel, and the curves represent the stress strain curves of each material. So the highest points in the curve, as I've mentioned earlier, are the ultimate. The specimen or the material will sustain deformation, but it will not break. Okay, so the end point of the curve is the so-called the fracture or the breaking point. So at this point, uh, deform, and it is the point outward, also called as the failure point. So let's go back in strain diagram of materials. Okay, so we have also the so-called elastic limit. So the elastic limit is the maximum stress to which a specimen may be subjected without a permanent deformation. And the line below this elastic limit can be linear or not. Okay. Terminology or a parameter in the stress strain curve that is coincident. This coincident with the elastic limit, the so-called proportional limit. The stress is proportional to the strain. Okay, so the elastic limit or below the elastic limit, the stress can be also proportional to the strain. But not all materials will go to a will proceed with deformation before ending uh, before going through a proportional limit of deformation. So elastic limit. So as you can see here in the we'll take a look here in the stress strain diagram. Uh, the curve for the elastic limit uh, can be the proportional limit plus there are also that they will undergo a significant deformation, but they can still return to its original length. There are also materials that their limit or their elastic limit is only limited in this when the stress is proportional to the strain. So that's the proportional limit. So while the elastic limit and the proportional limit are coincident with each other, they are different with depending on the material. But the majority of the length in the curve for the elastic limit and proportional limit follows the stress is proportional to the strain. Okay, now let's talk about this the proportional limit. Okay, so the proportional limit here in the stress strain curve as represented by point A. So from point O to point A, this is the proportional limit of the curve for a material. So below this limit, the stress is proportional to strain. Okay. So since stress is proportional to strain, if we express it into an equation, there must be a proportionality constant. So the proportionality constant below the proportional limit is the so-called is assigned as a constant, and it is the so-called modulus of elasticity. So, and this is represented by this equation, and thus the stress is equal to the this constant, the modulus of elasticity, and times the stress times the strain. Sorry. So since the deformation or the strain is the ratio of the elongation or the deformation and the original length. So it is basically dimensionless. Therefore, the unit of the modulus of elasticity is the same with the unit uh, of the stress. Okay, so thus the modulus of elasticity has units of uh, KSI, PSI, the same with the stress. Okay, so let's take a look at these equations for the total deformation. So this stress is equal to the modulus of elasticity times the strain. So since strain is equal to deformation over the total length, therefore we have this expression S is equal to the modulus of elasticity times the delta or the deformation over length, where this delta over L is the strain. Okay, so since the since stress is equal to or the unit stress is equal to the load over the cross-sectional area, so we will substitute that expression here. Okay, so F over A is equal to the modulus of elasticity times delta over L. So if we rearrange the equation, the deformation delta is equal to the load times length of the specimen all over cross-sectional area times the modulus of elasticity. So this equation, we will encounter more of this equation as we go on with the course. With regards to modulus of elasticity, it is important that you will be familiar with the values of the modulus of elasticity of commonly used engineering materials. So these engineering materials are the steel, wrought iron, and common values that is used throughout this course and also in practice. So for wrought iron, the modulus of elasticity in tension or shear is 30 raised to times 10 raised to the power of 6 psi, or this is 30,000 ksi. So, and for modulus of elasticity in shear or torsion, uh, which is represented or denoted by letter G, is 11.5 uh, times 10 raised to the power of 6 psi. This is for the steel. For wrought iron, which is also a another common engineering materials, is its modulus of elasticity in tension or compression is 28,000 ksi, while in shear or torsion is 10,000 ksi. So when solving problems involving modulus, most of the problems or some of the problems are do not give the values of the modulus of elasticity, since this is assumed that this is a constant that needs to be familiarized by engineers and engineering students. Please take note of these values of modulus of elasticity. Now there is a terminology that you may first hear in machine design, or I think some of you may have heard this somewhere. And this is the factor of safety, or the otherwise called the design factor. Okay, so this is denoted by letter N. Okay, so this is defined as a number that is divided into a criterion of strength in order to obtain a design criterion. Okay, so this will be hard to grasp for you as of now, but let's talk about the concept of the design factor. So the concept behind the usage of the factor of safety is that in design we cannot use the value of the ultimate strength or the yield strength of that material in the calculations right away, or without using a factor, because the subsequent results when using the ultimate strength or the yield strength would be too high risk for failure. So the designer should need to assign values below the ultimate strength or the yield strength so that the design would be safer. This design stress expressed by these equations. So this is denoted by S sub D. Ultimate strength and yield strength are divided by the design factor. Okay, so hence in these equations, the design stress uh, when using the or basing uh, from the ultimate strength is represented by this equation, and the design stress basing from the yield strength is represented by this. Okay, so you can see here that there are two design stresses. So yes, there are two design are the design factor based on ultimate strength and the design factor based on the yield strength, because the material has um, maximum possible two possible maximum strength. One is the ultimate strength, which will be based as the strength of a material, or the value of the strength of material before failure occurs, and or the shield strength is the strength of material that irreversible deformation of that particular material. There are criteria that must be considered in designing what design factor to be used. So take a look at table 1.1. So this can be located in page 20 of the reference book. Okay. Here in this table that There are four specific criterion in selecting the design factor. So if the type of loading or the foreseen type of loading for this element is a dead load, then there is a uh, corresponding design factor, which varies also for the type of material, whether it is a steel, ductile metal, or a cast iron, or a timber. So for repeated one direction gradual or ungradual loading, there's a corresponding descent factor for that. Also with repeated, reverse gradual, and the shock. Okay, so as you can see here, as the as the type of loading, as the type of loading involves higher degree, higher degree of shock or into a machine element, uh, the design factor increases. These uncertainties affect the magnitude of design factor. So designers cannot be certain as to what extent of the machine element's life can it handle a particular type of loading. So whether this machine element can be throughout its lifetime, whether it's only repeated. What if uh, there could be a shock load in its lifetime? So those are the uncertainties that needs to be considered by the designer. So with regards to loading, is there a possibility of shock loading, or will it be perpetually carry repeated gradual loads? Is the material completely homogeneous that we can assume uniformity of resistance? These questions constitute the uncertainties that are associated with designing machine elements. And thus, below are the factors that affect the magnitude the magnitude of the design factor. First is the material. A complete information about the material is not generally available. Yes, this is true. And this is true in practice. There will be possibility of internal flaws, improperly controlled treatment of the metal. This, if the designer is not completely certain with this material information, a higher design factor is recommended. 2. The size effect. It is known that failure of large parts occurs at lower stresses. Thus, it is suggested to use higher factor of safety uh, for large sizes of the same family of materials. So for bigger sizes of a particular machine part, even with the same family of materials, a higher descent factor is recommended. Next is the type of loading. So as what discussed earlier in the table 1.1, the criterion for that is the type of loading. So determining the service loading throughout the lifetime of a machine is practically impossible. Just what uh, the questions I've posed earlier. Will the type of loading be consistent throughout its lifetime? Is there a possibility of shock load? Those are the uncertainties with regards to the type of loading. Machines will undergo different types of loading in its lifetime. While estimates are essential, deciding deciding based on experience is way more practical. So when the nature of loading is known in some detail, a lower design factor is suggested. Otherwise, the designer should des- uh, the designer should decide on higher design factor. The computed stress. Computed average stress can be viewed with uh, considerable confidence, especially for simple stresses, because simple stresses are relatively easier to compute due to the nature or the uh, geometry of the elements or the the location of loading applied into these elements. However, for elements with complicated shapes and thus non-uniform stresses, uncertainty increases. One may determine stress experimentally, but the figure may deviate significantly or may not exist in the design. So, when there is uncertainty regarding the confidence of the computed stress, especially when dealing with complex shapes, non-homogeneous materials, and the location of loading, it is recommended to use higher descent factors. Next is the environment. Machines are typically operated in a dusty, corrosive, or oily working environment. These environments may result in cracking, roughened or smoothened material surface, which could considerably affect the material integrity. So thus, if throughout the lifetime of this machine element, if it is used with these environments that are uh, either dusty, corrosive, a higher design factor is also suggested. Next is the inspection. So the inspection revolves around the thoroughness and strictness of the material inspection before it is rolled out for usage in um, uh, the manufacturing of these machine elements. So this could also affect the magnitude of the design factor. So if it is known that the quality of inspection are not high, the higher design factor is also considered. The chance of an accidental load. Okay. So an impact force or accidental blow to a machine part may occur. Accidental blow is inevitable to any machine. So the design should be able to withstand some abrupt overload. So thus, when the designer decides decides a potential or a possibility of high impact load, factor should be used in order for the material to withstand some abrupt loading. Danger to life or property. Okay. Higher decision factors are desirable if there is a uh, high chance of life or property being endangered. So, and lastly is the price of the machine. Sometimes cheaper machines have lower factor of safety to reduce cost of materials and production. With all these factors mentioned regarding in deciding the design factors, the end point here is the judgment of the designer. So, if these design factors are considered practical, am I is the designer overestimating this possibility of these occurrences, uh, or is the designer underestimating the possibilities? So it is in the judgment. So this judgment refers to the experience of the designer. So this experience may also be derived uh, from their previous design experience, from actual experience in the machine shop, the found. As we go on in this course, you will observe that uh, each machine element has its own suggested design factor. So, and that of course considers some of the factors mentioned earlier. So, uh, a problem may give these design factors uh, based on the type of loading, or the problem shall say this is the type of loading throughout its lifetime, and thus we will look up these tables of suggested. These are the references that you'll be using in the problems for this course. So in the appendix starting in the page 561, you will see different tables such as table 81, 82, and these tables represent the properties of the materials, and the corresponding equations that is essential in the solution of the problems. So these are just some of the tables that we'll see in the appendix. In my next video, I will demonstrate how to solve a design problem under this topic of simple stresses. So thank you for listening, and that's all for